Hello everyone, I am Ehsan Moradi, a PhD student at University of Saskatchewan. In this video, I will present our work on the maximum clique problem in a grounded one-band string graphs. This is a joint work with Professor Mark Keil and Professor Debajyoti Mondal. We are all from Department of Computer Science at University of Saskatchewan. It is known that finding a maximum clique is NP-hard, even when it is restricted to geometric intersection graphs. For example, Keil and his colleagues proved that the maximum clique problem is NP-hard even for intersection graphs of two-dimensional arrays. Therefore, it is natural to investigate the problem complexity of simpler graph class. So we were motivated to examine whether the time complexity of the maximum clique problem for grounded segment graphs. These are graphs rising from the intersection of a set of straight line segments, where every segment has one endpoint on a grand horizontal line. While we could not settle the complexity for the segment graphs, we proved the maximum clique problem to be APX-hard for one-band grounded string graphs. Here on one-band grounded string is a polygonal chain with two segments, with one endpoint on a ground line. Furthermore, we obtained positive result for some subclasses of these graphs. Here is an overview of intersection graphs of various Lshapes, for which we have polynomial time algorithms for maximum clique. All these graphs classes are known to be subclasses of grounded segments graphs. Figure A illustrates a graph and B shows an intersection representation of the graph with one-sided Lshapes. The maximum clique size is 3, as we have a pairwise intersection of at most 3 Lshapes. Figure C and D are the intersection representations with two-sided Lshapes, where Lshapes can face both to the left or right. We can further restrict an L-shape to have same length, horizontal and vertical segments, which gives intersection representation with square L-shapes, as shown in Figure C. The table shows the running time for the maximum clique problem for this intersection of L-shapes. We first describe the APX hardness result. To prove that the maximum clique is APX-hard for grounded one-band strings, we reduce the maximum independent set problem in two subdivisions of cubic graphs, which is known to be APX-hard. Given an instance G of the independent set problem, we construct a grounded one-band string representation of the complement graph G bar. We show that a 1 minus epsilon approximation algorithm for the maximum clique in G bar would determine a 1 minus epsilon approximation for the maximum independent set in G, which will contradict the APX hardness of the maximum independent set. Therefore, we next show that G bar can be represented as an one-band grounded string. We first present original vertices as straight lines that intersect each other at a point P. For each edge, we then add two strings corresponding to the two division vertices. We will create the bend along the dashed lines. Every division vertex needs to be adjacent to all the original vertices, except for one it is adjacent in G. For example, the division vertex S1 CD should be adjacent to all original vertices except for C. Therefore, we start the corresponding one-band string to the left of C and bend at a dashed line to turn right and intersect all other vertices. Since the permutation along the ground line and the dashed line are opposite, we can always find a replacement for these division vertices to realize correct adjacencies. We design the dashed lines such that a pair of division vertices corresponding to an edge will intersect all the other division vertices. And finally, show that the coordinates of all the endpoints and endpoints of the strings are bounded by a polynomial size of the input. This completes the APX hardness result. We now show that the hardness holds even when the strings lie on a few lines. To prove the hardness result for few lines, we slightly modify the previous construction. We ensure that the bends and endpoints of the strings lie on at most 3 lines, L1, 2, and 3. We use the idea of representing the original strings with straight line segments between line L2 and L1. The division strings are used leveraging the idea that the permutation of the original vertices on the ground line is opposite to the permutation in line L1. Now we consider a subclass of one-bend presentation known as two-sided L-shaped graphs. We're given an order n cube dynamic programming for computing a maximum clique in such graphs. First, consider the property of a maximum clique. Assume that A is the highest and B is the second highest L-shape in the clique, and without loss of generality, assume that A is to the left of B. Then any other L-shape from the clique should be below the L. Assume that we have another L-shape C as a member of clique, then it needs to intersect A and B both, and should be to the left of A or right of B. In other words, no member of the clique can start between A and B. Now this forbidden region can grow if C be the next highest L-shape. If C is the left of A, then CB is forbidden. Otherwise, AC will be forbidden. Then an L-shape intersecting C and A must also intersect B, where B already belongs to the clique. One can thus continue adding a new L-shape that intersects the L-shapes, representing the current forbidden interval, without worrying about the L-shapes which have been chosen already. We use this idea to design the dynamic programming algorithm. Here is the recurrence relation for the dynamic programming. If there is no edge, then the maximum clique size is 1. Otherwise, let the AB denote a maximum clique, where AB or BA are the first and second highest L shapes, and A lies to the left of B. The dynamic table size is order n squared, and computing each entry requires linear time in the worst case. Therefore, the overall running time is order n cube. We now consider the case of two-sided squirrels. We again consider the property of a maximum clique. Assume that A is the lowest L shape in the clique, then all other L shapes of the clique must intersect the horizontal part of the A, which is labeled with H. Now we consider two vertical lines, Lx1 and Lx2, through the endpoints of H. We first show that every L shape that intersects H should intersect Lx1 or Lx2. For contradiction, consider the yellow L shape that intersects H but does not intersect Lx1 or Lx2. Then the horizontal segment of the L shape must have a length smaller than H. Therefore, this yellow L shape cannot be a square L shape, which is a contradiction. Now that we know every L shape that intersects H should intersect Lx1 or Lx2, then in the area R, which is green, we have parts of L shapes that can be considered as a circle graph. Now we know that we can solve circle graph maximum clique within n log a square n. Also, we can pre-compute the circle graph for every L shape in order n square log n time total. Therefore, we can find the maximum clique by considering every possible candidate L shape as the lowest L shape in overall n square log square and time. So again, we can say that given a set of n-grounded two-sided square shapes, one can find the maximum clique of the corresponding intersection graph in n square log square and time. We now consider the case for one-sided L-shapes. Assume that Q is the highest L-shape in the maximum clique. Then all other members of the clique should intersect vertical section of Q. We can use this idea to derive a straightforward recurrence relation. However, to compute the solution efficiently, we need some preprocessing. First, we pre-compute the intersection graph in n squared time. Then we maintain a sorted list of L shapes based on their origin and another sorted list based on their heights. The preprocessing takes order n squared time. We use the pre-computed data structure to find the L shapes that are intersecting a vertical segment, that is NQ, in linear time. Since NQ corresponds to a permutation graph, we can use an n log log n time algorithm for finding the maximum clique. And we can compute the maximum clique in order n square log log n time. Improving the time complexities of our algorithm would be interesting. The time complexity of finding maximum clique in a grounded outer segment graph is open, which seems to be a challenging problem to settle. Thank you very much for watching this presentation.